Okay, today we have a very important topic, cryptographic hash functions. Cryptographic hash functions also referred to as Swiss Army knife of cryptography because we use it everywhere. So for this reason, it is really important. So let's start with a basic definition. Then I will explain what I will expect from a cryptographic hash function. A hash function h is a keyless algorithm that takes a variable length input x and returns an output y of fixed length n. So we say the output is referred to as message digest, and n is here the message digest length. So idea is simple. You have an algorithm. It doesn't have any secret component. It doesn't use a secret key or anything. So everything known as an algorithm. And the input can have variable length. It can be 1 byte or 1 terabyte. It doesn't matter. But the output will be always will be fixed length, like 256 bits or 512 bits. Okay, depends on which hash function you use. So this is the basic definition of a hash function. But for a cryptographic hash function, I want some properties. Okay, so they're referred to as preimage resistance, second preimage resistance, and collision resistance. I will explain all of them one by one. Okay, but at the end of the day, what we also really want is that a hash function to behave like a random function. Okay, in other words, the output should look random. And actually, this idea is used in Bitcoin mining or similar ideas because you're expecting the output bits to be random zeros and ones. Okay, but let's focus on the cryptographic properties I would like. Let's start with preimage resistance. So if I give you an output y, it should be hard to find any input x that gives you hx equals to y. I'm saying any input because, as you can see, the input space is really large. I didn't limit it, actually. It is virtually infinite. But the output space is really small compared to this, because if I say that output has 256 bits, the output space can be, 2 to the 256. Yeah, so actually, you are mapping infinite elements to a smaller space. So for this reason, many different input will give you the same output. So this is inevitable. There will be collisions. But here, first thing I'm giving you the algorithm H. It is not secret. Okay, I give you the output. And actually, when you have the input, it is very easy to calculate Y. Okay, but without knowing X, I'm giving you Y. I'm asking you to find the inverse of the function, in other words. So for this reason, hash functions are also called one-way functions. When you have the input, it is very easy to calculate output. But when you have the output, it is very hard to go back. So what you can do, you can perform a brute force attack. So a generic attack will require around 2 to the n operations. Idea is as follows. Take random input x, calculate the h of x, and check if it gives you the desired y. So since the output length y has n bits, if you try 2 to the n random inputs, your expected rate becomes 1 at this point. So around some point, you should find some input that will give you y. Okay. So a good hash function shouldn't have any weaknesses so that you can find preimage with less than this many hash operations. That is the idea. So how we can use this? In practice, we use it as follows. In the past, when people created accounts, people kept these username and passwords in a file or in a database as plain text. So in 1990s, this is what happened on the internet. And due to security reasons, these databases leaked, and everybody's passwords also leaked. Okay, so many shopping web pages actually closed at the beginning of 2000 just due to this basic property. So what you could do is you could simply store the username and hash of the password. So whenever somebody wants to log in, you get the password, you calculate the hash, and check if it matches the one at your database. So this is sufficient to verify a password. But if the database leaks, hash of passwords leak, not the passwords themselves. So due to preimage resistance, by looking at the hash, people should not be able to guess your password. Of course, if it is really simple, a brute force can get your password, but If you choose a strong password, then this would be hard. So an attacker that captures the password file has to find a preimage. So if the hash function is preimage resistant, then you're okay. Okay. So of course, we will talk about this later, but let's give a note. Although I suggest this, so nowadays we don't simply use this. What we do is we also concatenate a random value called salt to the end of the password, then calculate the hash, but do not stop it. Take this hash value as input and put the hash function again. Do it again and again for thousands of times to make it harder for the attacker to perform brute force attacks, okay? So we will talk about this when we talk about password cracking, but I have to give a warning here because some people might think that this is okay to do. And for some reason, people are still doing this and they use MD5 and create an account. They just calculate the MD5 of it and put it in the database, which is a very dangerous idea. Let's see the second preimage resistance. Given an output y and an input x1 such that hx1 equals to y. So we know an input that gives us this output. So question is, can you find another input x2 that also gives you the same output y? Okay, so this is called second preimage resistance. A generic attack will require around 2 to the n operations. Again, you randomly choose x2 and check if it gives you this output y. So actually all of the blockchain or cryptocurrency security relies on this property. Also, any digital signature security also relies. So whenever you sign something or when you send a cryptocurrency to somebody, actually you're in programming code, you write that you are sending this amount of money to this person or this account, right? If I can modify the amount and still have the same hash value, then I can claim more money from it, okay? So this is a very important property. So let me also give an example where you can use this or how it might come in handy. So you're thinking that there is a virus in your computer. So when it is clean, you store the hashes of all your files and you just want to check if somebody will modify them, okay? So you calculate the hash of all of your files, keep it in a table in a different drive. If the attacker modifies the files, for instance, put a malicious code inside them, and can still obtain the same hash value, then the attacker can fool you, right? Because the hash will be the same, but the file will have a malicious code inside it. But of course, calculating the hash of your files also might come in handy. For instance, in your drive, you want to know if you duplicated a few files because you put them in the past in many different folders, and you want to know if you have duplicate files on your computer. A simple way to do it, hash all of your files, then sort them. When sorted, if two same values come next to each other, you say that, okay, there are two files in two different folders. So, you can delete them if you want. So the third property, which is also important, so it is called collision resistance, and it says that it should be hard to find two inputs, x1 and x2, such that hx1 equals to hx2 equals to y. Okay. So you might think that, okay, this is the same thing like the previous one, right? Because in the second preimage resistance, I said a similar thing, right? But here, the most important difference is that here x1 is fixed, okay? You have no control over it. I'm giving you the x1, h. So once you have the x1 and h, it is easy to calculate y. Now your aim here is to find another x2, okay? In the second preimage resistance. But in our third property, I'm not fixing x1 or x2. I'm only giving you a hash function. So you have more freedom. You're trying to find two inputs that give the same output, okay? So for this reason, a generic attack actually requires less operations here, 2 to the n over 2. So square root of the previous generic attack. So this is a lot faster because if n is 128 bits, in the previous properties, I need to perform 2 to the 128 operations, which is almost impossible for our computational power. But once it is all divided by 2, it reduces to 2 to the 64, which is within our reach. We can perform this many operations, okay? So this is due to birthday paradox, which I will explain in a minute, okay? So Why this property is important? Think about a scenario where hacker prepares two versions of a software driver for an operating system where X1 is correct and X2 contains a backdoor that allows access to machine, but both of these versions have the same hash value. Okay, since the attacker has control on both files, they put a malicious code inside the driver, but then try to modify it so that both of them gives you the same hash value. So hacker sends the correct version, which doesn't have a malicious code in it, X1, to the operating system company for inspection. So for instance, if it is a Windows driver, you send it to Microsoft. Microsoft checks for viruses. And if there isn't any, Microsoft signs H of X1, because X1 might be really huge, right? Maybe it's a 1 gigabyte of a driver. So instead of signing a 1 gigabyte document, actually, they sign the hash of it, which is really small. So that whenever you want to install it, this driver, actually your operating system checks the signature and the hash of this file and say that, okay, this is a secure file because the operating system company already signed it. But what the hacker does is that they distribute X2. They put it on their web page X2, so you download it. So whenever you try to install it, operating system company verifies this signature with their public key. So your operating system checks if that signature is valid. So it will be valid because H of X2 is the same as X1. Since H of X1 equals to H of X2, the signature works. So you don't understand that there's a virus behind it or a backdoor. So actually this idea is used in Flame malware with MD5 hash function. Okay, we will see them when we talk about these dedicated designs. So let me finish it with birthday paradox and explain why it is easier to find collisions than second preimages. So birthday paradox is a simple question saying that how many people need to be in a room before it is more likely than not at least two people share a birthday. Okay, this means that you keep putting people inside the room, and after how many people are inside the room, it is there's more than probability 1/2 that there are two people in the room with the same birthday. Okay, so when this is asked, people think that since there are 365 days in a year, they divide it by 2 and say that probably we need like 180 people in the room so that they have a same birthday. But here, the answer is 23. This is why we call it a paradox, because people were expecting, more than 100 people or so. So let's calculate this. Consider the probability that nobody shares a birthday, okay? The first person in the group has a birthday on a given day. So the room is initially empty. So you put a person in the room, since they cannot share their birthday with anybody else because there isn't anybody else. Here the probability is 1 that nobody shares a birthday in that room. To avoid a match, when you put the second person, this person should have a birthday that is different than this first person, right? So this has a probability of 364 divided by 365. So it's 0.999, right? So it's a very high probability. You put the third person here, but this person can share their birthday with this one and this one. So this is why now you end up with 363 days and so on. So if you do this after t%, the probability that nobody shares a birthday is this, okay? So the probability that we don't have any matches among a group of t people is this. So if you subtract this from 1, that will be the probability of people having a birthday in the room. So the probability p that we have at least one match is 1 minus this, okay? So, take t equals to 1, take t equals to 2, then calculate what happens to p. You will realize that when t is equals to 23, this probability is larger than 1/2. In other words, when t equals to 23, probability becomes 0.507. So this is like flipping a coin. But after you increase the number of people, like 20, make it to 25, 26, this probability actually increases in a dramatic way. So if there are like 30% or more, most probably you have a shared birthday, okay? So for this reason, The more general case where we have t people and n possible birthdays, it can be shown that probability is 1 minus e to the minus t squared divided by 2n. So when there are n possibilities, recall our hash functions, we have an output that is n bits, right? So we have 2 to the n possibilities actually. So after making approximately square root of choices, we have a collision. This is why we say that 2 to the n over 2 is enough to have a collision due to this square root, okay? It comes from this, and when n goes to infinity, it goes to this and so on. So it's by calculus, you can easily calculate these values. So basic idea is that people think that this is a paradox because they think that they fix their birthday and they try to imagine if anybody that enters the room has a birthday with them. This is actually second premise because they fixed their birthday, right? X1 here. So they're trying to find another X2. This is why that they think that this problem will be hard. There should be a lot of people. But actually, when somebody enters the room, they can share their birthday with anybody else in the room. So the probability increases kind of dramatically. This is why it is a paradox, okay? Let's finish with some use cases. For instance, how can you use hash functions? A forensic investigator would like to have a very small digital fingerprint of every storage device at a crime scene to detect if any modification to these drives happen in the future. So this is actually what legal process is. Instead of, cloning all of the drives and so on, you simply take the hash of these devices. So in the future, you can detect if somebody malicious to put something inside these drives or not, okay? Another use case I already mentioned a few minutes ago, you want to find all duplicate files in your disk, simply calculate hash of them, sort them, and if there are duplicates, you will see same values appearing twice in this list. Another case where actually this is how the cloud works. Dropbox, Google Drive or Gmail works like this. Millions of users upload the same file to cloud, but cloud provider wants to store only a single copy and therefore limit the upload of the same file to one to say bandwidth. So this way they just check the hash of the file. If they already have the file, if two users put it, only one of them is stored, and they only store who can access that file or not. So without hash functions, actually we couldn't have this kind of cloud services anyway. Also, we couldn't have any blockchain technology or cryptocurrencies. Another case is an intelligence agency wants to give a list of illegal files to forensic investigators without sharing the files themselves. So they only share the hash value, saying that any file with this hash value is, illegal. So they tell the, forensic investigator, just check if you see these files in any case, okay? So this way, forensic investigators doesn't know what the files are, but they have a list of them as hashes, and they check at the crime scene. Similarly, a forensic investigator wants to check if this contains any illegal files that are pre-obtained. They simply calculate the hash of these files and check, okay? Actually, this is how cloud works, by the way. For instance, if you have any copyrighted material, like a movie file on your computer, and if you try to upload it to Dropbox, Dropbox will reject it, saying that this is a copyrighted material, and they won't store it. And the file might be a few gigabytes, but the instant you put it on your Dropbox folder, they will look at the hash of it, and then they will give a warning in less than a second saying that they are not going to store it. This is illegal, okay? You can do this for copyrighted material or illegal files like child pornography and so on. This is actually how the forensic investigators or intelligence agencies detect these kind of files. But of course, don't forget that if you make a small modification to the file, then the hash changes. So if you have an image which is illegal, like child pornography, you know the hash of it. So we can always detect it. So cloud services do not store this file. But if that person, a malicious person who wants to store it, might change one pixel, and the hash will be different, so they can keep storing it. So this is why some regulations try to detect also these files, okay? And you cannot do manually, so maybe with the help of an AI, you can try to detect this, okay? But of course, this will be meaning that you are scanning other people's files. Let's finish it with this final word. Hash functions have many uses in cryptography and are considered the Swiss Army knife of cryptography. Some of them are digital signatures. As I mentioned, you don't sign a message itself, you sign the hash of it. Message authentication codes, pseudo-random number generators, key derivation functions, where you want to use a secret key, but you don't want to generate it by flipping coins to get zeros and ones. Instead, you get a strong password, and hashing it thousands of times. The resulting hash value is used as your secret key. Think about this in full disk encryption. You choose a strong password, and from your password, they calculate hash of it thousands of times and obtain a 256-bit output, then use it as AES 256-bit secret key, so that whenever you want to turn on your computer, you have to re-enter your password to generate that key so that you can access the files and so on. So from a password, you turn it into a secret key. So these key derivation functions are really useful, and they are used in many places.